Dear students, welcome back to the fault simulation chapter. We have introduced serial fault simulation and parallel fault simulation. In this video, we are going to introduce an interesting idea, a deductive fault simulation, which was proposed in 1972 after parallel fault simulation. In our previous video, we have shown this flow of fault simulation. It has two loops. There is a loop of faults and there is a loop of patterns. Because we have two levels of loops, so fault simulation is very slow. Can we do better? The idea of deductive fault simulation is to use logic deduction instead of circuit simulation to speed up fault simulation. In deductive fault simulation, there is a fault list for each signal A denoted as LA. A fault alpha is in the fault list LA if A's value changes in the presence of fault alpha. For example, in this circuit, we apply a test pattern A equal to 0, B equal to 1. The fault list of A is denoted as LA, has only one fault. The A stuck at one fault. In this picture, A/1 denotes the fault A stuck at 1. Because if A is stuck at 1, the value of A would be changed to 1. That's the reason why A stuck at 1 fault is in LA. Similarly, the fault list of B contains one fault, B stuck at 0 fault. The fault list is propagated through a gate. When A stuck at 1, output C would be changed to 1. So A stuck at 1 is propagated through this AND gate. So A stuck at 1 fault appears in the output fault list LC. On the contrary, because A is the controlling value 0, B is non-controlling value, so the value of output will not change when B is stuck at 0. So B stuck at 0 fault is not propagated to the output fault list LC because C is unchanged even when B is stuck at 0. Please note that C stuck at 1 fault also appear in the fault list LC because when C is stuck at 1, the value of C will be changed to 1. If we propagate the fault list to the primary output, then we can easily figure out which fault can be detected. During the whole process, we use logic deduction instead of circuit simulation. So the good news is that we don't need a loop of fault anymore. Everything can be done all at once. This is a very nice idea. The procedure of a deductive fault simulation is like this. Step 1. Apply a test pattern. Perform a fault-free logic simulation. Step 2. For each primary input, we attach a fault list. The stuck-at value is opposite to its good value. For example, if A good value is 0, then we attach A stuck at 1 fault in the fault list. If the good value of B is 1, we attach B stuck at 0 fault in the fault list. And then step number 3, we propagate the fault list from PI to PO. The rule of fault list propagation is dependent on the gate type and the gate input. The detail will be shown in the next slide. And finally, when we reach the primary output, a fault is detected if it appears in the fault list of any primary output. So this slide shows the fault list propagation rules. For an inverter, suppose the good value is 0 and the output is 1. The output fault list is equal to the input fault list LA plus the C stuck at 0 fault. Because any fault that flip the value of A can also flip the value of C. Similarly, when A is 1, the output fault list is equal to LA union C stuck at 1 fault. In our notation, this symbol represents a set union. For the AND gate, suppose that both A and B are 1, so the output C is 1. In this case, the output fault list LC is equal to the union of LA and LB, because any fault that flip either A or B can flip the output C. So we take the union of two non-controlling input. And don't forget, the output C stuck at 0 fault is also included in the output fault list. Now, suppose that the good value of A is 0 and the B is 0, so the output C is 0. In this case, the output fault list LC is equal to the intersection of LA and the LB, because even if we flip only A, the output will not be changed. The only way to change output C is to flip both A and B. That's why we take the intersection of LA and the LB. This symbol represents a set intersection. And don't forget, we have C stuck at 1 fault at the output. Now, suppose that A is a controlling value 0, B is non-controlling value 1. In this case, we take the fault list of LA minus the fault list of LB. This is because A is a controlling value. If A is flipped to 1, the output would be flipped to 1. But B must remain non-controlling. So we need to have LA minus LB. This notation represents that we remove the intersection of LA and LB from the set of LA. So the shaded part represent LA minus LB. And don't forget, we need to add C stuck at 1 fault at the output. For a fan out, when A is 0, B and C are both 0. So the output fault list LC is equal to LA union C stuck at 1 fault. But the output fault list LB is LA union B stuck at 1 fault. This is because fan-out faults are not equivalent for single stuck at 4 model. Now, it's time for you to work on a quiz. For this OR gate, Please generate the output for list. Please pause the video and work on this problem. Now, are you finished yet? The answer is like this. When both A and B are controlling value, we take the intersection of LA and LB. When both A and B are non-controlling 0, we take the union. This is actually the dual of the propagation rule of AND gate. Have you got it correctly? Now, let's see the flowchart of deductive fault simulation. Given a collapsed fault list of the whole circuit F, we apply a new pattern. We run a fault-free simulation, propagate the fault list through the gate, and we drop the detective fault from F. And we check if there is no more fault in the fault list, then we are done. Otherwise, we continue to the next pattern. Please note that there is only one loop of pattern. There is no loop of faults. Now we will demonstrate deductive fault simulation using the same example circuit. Please note that in this demonstration, we use all the 18 uncollapsed faults for explanation purpose. Initially, there are 18 faults in the circuit, and we apply the first test pattern: A equal to 0, B equal to 1, and C equal to 0. So initially, the fault list of A is A stuck at 1, 4, and LB equal to B stuck at 0, 4, and the LC equals to C stuck at 1, 4. And then we can propagate the fault list through the OR gate G1. Because B is non-controlling value, so LB is propagated through E, and LC is not propagated. And then we propagate this through the fan out, so we now have B stuck at 0, E stuck at 0, and F stuck at 0. And then we propagate this through the inverter G3, so now we have 4 faults at the output of J. And for the AND gate G2, because A is a controlling value 0, L is non-controlling value 1, so the fault list LA is propagated to the output H. But the fault list of L is not propagated. Now let's consider this NOR gate. Because both H and J are non-controlling value, so we take the union of LH and LJ. Finally, we add K stuck at 0, 4. So now we have 7 faults at the primary output. So these 7 faults are detected. The detected faults are dropped, and we have 11 faults remains to be detected. Now let's apply the second pattern P2, where A is 0, B is 0, and C is 1. So now the LA fault list is empty. Why? Because A stuck at 4 has already been detected by pattern 1, so we don't need to consider it anymore. And similarly, we can propagate the fault list of C to J and then eventually to the primary output. So one fault is detected by pattern P2. So we still have 10 faults remain to be detected. Now we apply pattern P3 where A is equal to 1, B is 0, and C is 0. And we can propagate the fault list in the same way. Now for the output G4 NOR gate, because H is non-controlling and J is controlling value, so when J is flipped, output would be flipped. So we take the fault list of LJ minus the fault list of LH. So we have F stuck at 1 and J stuck at 1 plus K stuck at 1 fault. So 3 more faults are detected by pattern P3. So overall, we can detect 11 faults out of 18 faults. The fault coverage is 61% for these 3 test patterns. Now it's time for you to work on an exercise. Let's apply test pattern 101 to this circuit. Please perform deductive fault simulation. For simplicity, let's consider only 3 faults. A stuck at 0, B stuck at 1, and C stuck at 0. Please show us which faults are detected. Please pause the video and work on the quiz. Okay, are you finished yet? First, let's perform a logic simulation. The value of E is 1, and F is 1, L is 0, output K is 1. So now we can propagate the fault list B stuck at 1 4 here, and we take the union of B stuck at 1 and C stuck at 0. For this AND gate G1, because B is controlling 0, so the fault list of A is not propagated to the output. So the fault list of L is equal to B stuck at 1. Now at the output OR gate G4, because L is non-controlling, F is a controlling value, so the fault list at output K is equal to LF minus LL, which is C stuck at 0,4. So C stuck at 0,4 is detected. Have you got it correctly? Now, let's have a summary of this video. The idea of deductive fault simulation is to use logic deduction instead of circuit simulation. The advantage of deductive fault simulation is to eliminate the loop of faults. However, there are several drawbacks of this technique. First, there is a big problem with multiple value logic, like unknown or high impedance. The fault list propagation rule becomes very complicated in the presence of unknowns. And the second problem is difficult memory management, because we don't know how many faults will be detected in every simulation, so we don't know how much memory to allocate. The memory requirement is unpredictable, which is a very bad thing for large circuits. Also, there are many set union and set intersection operations, which are difficult for large designs. Finally, the deductive fault simulation does not consider delay, so it's not suitable for delay fault. In conclusion, deductive fault simulation is very interesting in theory, but unfortunately it's not very useful in practice. Before we end this video, we have some interesting FFT for you to think about. Question number 1. We mentioned many set operations in deductive fault simulation. So, what data structure is suitable to implement the fault list? And what is the time complexity for set union and set intersection? Question number 2. How can we propagate the fault list in the presence of unknowns? For example, if A is a unknown for the inverter input, what would the output fault list LC be? For this AND gate, if any of the input is unknown or both of the inputs are unknown, so what would be the LC? These are two interesting questions for you to think about. I hope you enjoyed this video. Thank you.